Okay. Any questions about last time? Talked about set cover. So an example where greedy doesn't work, but gives us sort of a solution with a good quality. And then in the end, we started talking about dynamic programming, where we said that greedy is good and it's efficient, but it does require this very specific structure where we make sort of a choice that looks the best at the moment. And then we just continue with one subproblem. And not all problems have this structure. So some problems we can solve easily using this very simple yet efficient scheme in greedy. And so we said an alternative framework is dynamic programming, where we, in general, follow a different scheme. We typically try to, maybe I have someone in the waiting room, where we try to decompose our problem first into smaller subproblems, and then try to solve these subproblems one after the other, starting with the smallest one. And then once we have this solution, the solutions to the smaller problems, we try to use that information, gather it to come up with a solution to the original problem. So the general setup, therefore, in dynamic programming looks as follows. This general setting works as follows. We have, we decompose our problem into smaller subproblems. We stopped last time. Bigger. So this is the general steps in dynamic programming. You first break the problem into smaller subproblems. And then we tackle these subproblems first, starting with the smallest problem. This is what's called generally bottom up. And then we use this information that we gain from these smaller subproblems to solve larger subproblems. Okay, so that's the general high-level idea of dynamic programming. It's a bit abstract, so let's look at an example, sort of a very simple problem that we can solve using dynamic programming, which is called the longest increasing subsequence. So in this problem, we are given a sequence of numbers, A1 through AN. And you want to find an increasing subsequence. I'll show in a second what that means. Find an increasing subsequence. Which we denote by AI1 through AIK. With I1 being strictly smaller than I2, being strictly smaller, and so on, up to IK. So this is what it means to be a subsequence. We can pick elements, but we have to preserve the order of these elements. And it's an increasing subsequence. So what this increasing here means is that A1 is strictly smaller than A2, which is strictly smaller than A3, and so on. I'll show you an example. And we want to find the one with maximum K, so the largest sequence that satisfies these conditions. So with largest K. So here's an example to make this more clear. Let's say we are given the following numbers A1 through AN. In this case, A1 is equal to 5, A2 is 2, 8, 6, 3, 6, 9, 7. Then the longer, yeah? Conceptually, we don't care really at this point. It's more like we don't really also wonder about the algorithm. We do wonder about the algorithm, but not about the implementation. So these are, yeah, we can assume small enough numbers, but it doesn't make a big difference really, or any difference. So conceptually, what you're looking for is a subsequence, sort of increasing numbers. So in this case, what we could have, we could start at number 2 here, and then go to number 3. So the 3 is to the right of 2. This is why this is a subsequence, and 3 is larger than 2. This is why it's an increasing subsequence. And we can continue this. We can go from 3 to 6, because again, 6 is to the right of 3, and 6 is larger than 3. And then from 6, we cannot go to 9, obviously, because, we could, of course, go to 9. We have the choice, really. If you go to 9, we can't go to 7, or we can directly go to 7. So in terms of the length, it doesn't make a difference. But again, 7 is larger than 6, and it's to the right of 6, and that's why this is a valid subsequence. And as far as I can see, this is also the longest increasing subsequence. So in this particular example, the subsequence is simply 2, 3, 6, and 7. So is everyone clear about the problem setup, what we're trying to solve in this case? The subsequence of increasing numbers. So to understand this solution space a bit better, let's try to visualize all possible transitions between 2 numbers in this sequence. Let me draw this again, the same sequence of numbers. 5, 2, 8, 6, 3, 6, 9, and 7. And so I start with number 5 from the left, and I look to the right, and I want to know where I could go next from 5. I can't go to 2 because 2 is smaller than 5. I could go to 8. So I indicate this by this arrow here, or by this edge, if you will, directed edge that points from 5 to 8. I could also go from 5 to 6. I could go to the second 6 here in the sequence, and I go to 9, and I could go to 7. So these are all permissible transitions from 5 to a number to the right. If I look at the next element 2, I could go straight to 8, to 6, to 3, 6, 9, 7. So 2 is the smallest number. That's why I can go really everywhere to the right. That's not true for 8. For 8, I can go only to 1 number, namely 9. Yeah. From 6, I could go to 7 and to 9. So I can go to 9 and to 7 from 6. Same for this 6. And so on. No, we're done. 9 cannot go anywhere. So this is the graph that shows basically all possible transitions between 2 numbers. And then you probably can see that every increasing subsequence in the sequence of numbers corresponds to what in this graph? So let's think about this as a graph where the numbers correspond to nodes, and they have these directed edges. it is a tree, but even simpler than that. What? Someone said something I heard. It's a roots. No, we have a path, right? Acyclic. It's acyclic. I mean, a path is always acyclic, so it's just a path, a simple path. Because whenever you take a subsequence, you basically have to do this by following these edges, right? So the sequence that we had before starts from 2, goes to 3. So we follow this edge. And from 3, we take the edge to 6, which I apparently forgot to draw here. So there should be an edge from 3 to 6. I actually didn't draw any edge out going from 3. So there's a couple of more missing, but I'm sure you have done this right. So we're going from, in this case, 2 to 3, and then 3 to 6, and then 6 to 7. I mean, here is the edge. So this subsequence simply corresponds to a path in this graph. And there's a one-to-one correspondence. And in particular, the longest increasing subsequence will then correspond to the longest path. Exactly. So we have to do, what we have to find is the longest path in this graph. And how do we find the longest path in such a graph, which is acyclic? So this is, in this case, a DAG, because I only have edges from the left to the right, so I cannot create any cycle. Well, we will discover that it has a similar property that we require for most greedy algorithms. It has this optimal substructure property. Because if you look at the longest path that ends at the very right, it's, let's say, node 7 or number 7, this longest path has to come through one of its predecessors, right? So we have to reach 7 somehow, and we can only do this through an edge that connects to 7. So we have to go to one of the predecessors, which is 6, 3, 2, and 5. And then once we look back and we know which predecessor lies on the longest path, we have to then again find the longest path all the way up to that predecessor. So in that sense, we have this optimal substructure. Finding the longest path from 7 basically depends on the longest path to any of its predecessors. So we would have to go back and then go to the predecessor, again, solve the same problem, try to find the longest path to a predecessor, and so on. But I'm sure you will agree it's much easier to think about this from left to right instead of right to left. Because now if I try to make a similar argument for the first element, which is 5, the longest path to 5, well, again, it depends on all its predecessors, but it doesn't have any. So it's simply 1. So the longest path that ends at 5 will be 1. The same is true for number 2. There's no predecessor of 2, so we only have a path of length 1 that ends in 2. But then it's getting more interesting, because now if you're looking at number 8, 8 has 2 predecessors, namely 2 and 5. So by the argument before, we would have to say, well, the longest path to 8 or ending at 8 has to come through either 2 or through 5, based on the structure of this graph. So we'll look up the longest path to 5 and see it's 1 plus that 1 edge to 8, so it's going to be 2. And if I were to go through 2, I would have to again look up the longest path up to 2, which is 1 plus this 1 additional edge to 8, which gives again a path of length 2. And I keep doing this basically from left to right, and this is what it intuitively means to solve this problem bottom up. Okay, let's try to write this down a bit more carefully. So, but you can see that the main ingredient in this is that we have defined a subproblem. So this is what I originally said. We have to define smaller problems that we want to solve first before we build up solutions to larger problems. And in the way I phrased it, our subproblems are simply the longest paths that end at a certain element in the sequence. Okay, so let's call this LJ. So let's define, you will see in a second what we do with that. Let L of J denote the length of the longest path ending at J. Okay, that's just what we considered so far. So this is the length of the longest path ending at J. And we said that we want to solve this bottom up, meaning in this case from left to right. And then our usual pseudocode notation, it means that we have to iterate through numbers from left to right, from 1 to n. So we would go for j equal 1 all the way to n. And then we would see that Lj, the longest path ending at j, would be equal to so we have the extra edge coming from our predecessor, which contributes a 1 plus, and any suggestion what I have to write here? So what is the longest path ending at j? We have this 1 extra edge, and then we said that we can only go through a predecessor. So we have to look at edges ij in this case. So let's look at all li's with ij being an edge in this graph. So what's missing here in the space? What is Lj? Yeah. J minus 1, but so predecessor doesn't mean that it's the element to the left. It means that it's connected through an edge, because in a subsequence you can come from anywhere to the left. So what would I have to fill here between the 1 and the li to make this whole thing meaningful? We have this 1 extra edge from one of the predecessors, meaning from one of the nodes that connects my node with an edge. And all these transitions are permissible. The maximum, exactly. So we take the maximum over all these li's that connects basically to Lj. That would be a plus maximum over all these li's over all li's. This is, and what do I return? Once I have computed this for all j's, and I have basically checked all predecessors and computed this numbers from left to right, what do I return in the end? What's the result? Yeah. Max over all the j's, really, right? So again, you take the maximum elements, the maximum Lj over all j's, really. Yeah, so this is how we compute the longest increasing subsequence using dynamic programming. So and again, so now that you have seen an example, try to connect this to this abstract scheme in the very beginning. We said we want to divide this problem into smaller subproblems, which we have done here by looking at basically Lj's. So this is our small subproblem. And they get smaller the smaller the j is. So we have basically L1, which is the longest path ending in 1, and L2 and so on. So these are our subproblems. And then we have to order them such that I can traverse these subproblems in a specific order. And in this particular problem, we traverse these problems simply from left to right. And if I do this in this order, then I can always describe how I compute a solution to my current problem based on the smaller problems that I already have computed. Right? And this is what I do here. So I always have, I look at predecessors of j that are connected through an edge, and I take the maximum. And then this equation tells me basically what the relation is between the solution to my problem to the solutions of the subproblems. Namely, you just take the max and add 1. So this is the essence really of dynamic programming. So in different problems, subproblems will be more or less complex, and it will be more or less difficult to come up with such subproblems. The relations between these subproblems might be much more complicated or complex, let's say. But this is the general principle of dynamic programming. So Let's conceptualize this graph notion here that I have sort of skimmed over. So I drew this thing that looked like a graph, but I never really introduced this as a graph. But this is what's known in this context as a subproblem graph. Which in this case is a directed acyclic graph, where the vertices in this graph correspond to the subproblems that we're trying to solve. And we have edges between two subproblems, x and y, whenever the solution for x depends on the solution for y. We have edges x, y, which will indicate that an optimal solution for x will require you to first solve the subproblem corresponding to y. Can everyone see how this corresponds to the subproblems and to the graph that we showed before? Our subproblems were these LJs, and we had edges that correspond directly to these edges that I have described here, except that in the definition of the subproblem graph, the direction of these edges is defined in the reverse direction. So before we had an edge from x to y, or from two numbers whenever I could make this transition, but really the meaning of these edges are now sort of in the reverse order. That means that Lj would depend on Li, and then we would have an edge in the opposite direction. But the structure is exactly the same. It's just the interpretation of the edges is sort of switched around. And so based on this, we can draw what's called a subproblem graph. So you would have, let's say, for subproblems, A, B, C, D. So you have A, B, C, and D. And then we have arrows, for example, from A to B, indicating that in order to solve A, you first have to solve B. Same for B to C and C to D. And on top of that, A might also depend on C and also on D. And B might also depend on D. We have this dependency we denote by these edges. And the way we solve such a subproblem graph in dynamic programming is bottom up, meaning in this direction. So this is what it means to solve this whole thing bottom up. And sort of the more formal term for this traversal in this ordering is in reverse topological sort. I believe you have heard of a topological sorting before. Yeah. And this is sort of the reverse topological sort because you traverse these edges in opposite direction. So this is basically in reverse topological sort, which means nothing else than before solving a problem, make sure that you have solved all the subproblems that this problem depends on. So a quick note about the complexity of solving such a subproblem graph in reverse topological sort. So the time to solve a subproblem, considering the subproblem graph, typically is proportional to the number of outgoing edges, because it's all the subproblems that it depends on. In the longest increasing subsequence, that simply meant that we have to look at all the predecessors and take the maximum. So we had to look at all these edges, and the time will be proportional to the number of such edges. Time to solve a subproblem is proportional to the number of outgoing edges. Here outgoing, but in the previous example, outgoing would mean incoming edges. This is basically the number of predecessors through which you can reach a certain number. Outgoing edges. And the number of subproblems is equal to the number of vertices in this representation. And that means that the running time will be linear in what exactly then? So based on all this, so we have a certain number of problems, and for every problem, we have the dependence basically on the number of outgoing edges. So overall, the running time will be linear in, what would you say? So you have to solve all the subproblems, and you solve them once. And every subproblem has a running time that depends on the number of outgoing edges. So overall, order what? V plus E, exactly. So it's the total number of edges in your graph, plus the number of nodes, because you have some constant work also in your nodes. In our example, previously, we had to add 1 to the maximum. This is sort of what you have to do, but it depends on all, the maximum you take basically depends on all outgoing edges. So it's the number of edges plus the number of nodes. So it's going to be linear in number of vertices plus number of edges in this graph. So what's the worst case then in terms of the longest increasing subsequence? In terms of running time, I meant. How many edges can this subproblem graph have in the sort of the worst case scenario for longest increasing subsequence? It's sorted, right? So it's in increasing order sorted. Then every element would have an edge to every predecessor, and you would have n squared many edges. And then the running time of this would be n squared. And then the best case scenario, I guess in this case, it's sort of if it's reverse sorted, then you don't have any edges really, because you cannot ever make a transition to the right because these numbers are all smaller. Okay, so this is our first insights based on this example. Now let's try to come up with a general scheme how to design a dynamic program. So what are the ingredients that we have to look for? Essentially, they're all there already. But this example will show that one has to be careful a bit with this. So the first one is, and we have seen this before, optimal substructure, which simply means that in finding the optimal solution to your problem, you can rely on the optimal solution of subproblems. So this is similar to greedy. The optimal solution to a problem contains the optimal solution to subproblems. We had this before, but just for completeness. And this is, in effect, allows you to draw this subproblem graph. This is the whole idea to visualize this dependent structure. This is what an edge really means in this graph. But let me give you an example of this. And if you want to find the unweighted shortest path in a graph, and in an unweighted case, a shortest path is always simple. It doesn't traverse the same node twice because you would introduce a cycle, and getting rid of the cycle would shorten the length of this path. So the shortest path will be simple. Does this have optimal substructure or not? What is your guess? I actually shouldn't guess. I think you should know by now. Because I think that's what you also, I mean, you probably talked about or learned Dijkstra. So shortest path clearly has optimal substructure. So let's see why. Or exactly what that means. So let me write down the shortest path from a vertex U to a vertex V. So if I call this shortest from U to V, let's write it down like this. So we start at vertex U and we go to a couple of other vertices along this path, and at some point reach some vertex W. Then we continue from W through some other intermediate vertices and finally reach vertex V. And then essentially we have to look at these paths basically from, for example, W to V. And what shortest substructure means is that the shortest path from U to V must include also the shortest path from W to V in this case. And it's very simple to see because you can again apply this cut and paste argument, because if there was a shorter path from W to V, you could just replace this with the current path from W to V and obtain something that is overall shorter than your previous path. And that's why you have this optimal substructure property. So this one here must be shortest path. How about another example? We look at the unweighted longest simple path. So you're going to look for a simple path that doesn't visit any vertex more than once. And any guess, does it have optimal substructure or not? The longest path. It doesn't? Oh, okay. Why not? No. It doesn't have to reach. I'm just looking for the longest path from some vertex U to some vertex V. Any other suggestions? It sounds very similar to the shortest path problem, right? And you would think that you could apply a very similar cut and paste argument, that if you look sort of some subpath, if this is not the longest, you could cut and paste for a longer one and get something better. But in fact, in this case, it's not. It doesn't have optimal substructure, and this is why I wanted to show this, to give you some intuition, or let's say warning that this is sometimes a bit more subtle, this property, and you have to be careful about interpreting this. Because if you look at the following example, and this is now I can call it actually the way I wanted to call it. This is a counter example. So let's say we have this following graph is 4 vertices. We have P and Q and R and S, and we have edges between all pairs in both directions. Now let's look at the longest path from P to R in this graph. The longest path from P to R is, well, starting at P, then going to Q, then S, and then R. So that's clearly the longest path. It uses 3 edges. But in this case, if you look at this subpath from S to R, then this is not the longest path from S to R, right? Because in S, if you wanted to go from S to R, we would have to go in this direction. We would have to go to P, Q to P, and then to R. But in this solution, we only take the shortcut really from S to R. So we take this route, which is clearly not the longest path between S and R. And this is exactly contradicting or violating what it means to have optimal substructure. So the longest path from P to R doesn't include or is not based on the longest path between sort of the subpaths. So this one here is not the longest path. And that's why this doesn't have optimal substructure. And so on a high level, what distinguishes these two problems, even though they sound so similar, is that the subproblems are not independent in the case of longest path. They are in the case of shortest path. But when you compute the longest path, for example, from S to R, you would, as I said before, you would go in this direction. But then if you wanted to attach the longest path from P to S, or you wanted to concatenate these two, from P to S, you would like to reuse some of the vertices that you already have used in the other subpath. And so the two subpaths that you want to use to stick them together to the longest path of the entire problem, they're not independent. And this dependence sort of kills this optimal substructure. So that's why you cannot rely on optimal solutions of these subproblems. And this is in contrast to the shortest path problem. The nature of this problem doesn't really allow for any dependence between these shortest paths. Because if you had a node that you would use in both subpaths, in both shortest subpaths, then you would introduce a cycle, and the cycle means that cutting it out would make the whole thing shorter. So a shortest path doesn't want to reuse any cycles really between subpaths. And that's why you get this part for free. And the shortest path doesn't have this dependence between subpaths, and that's why this has this nice optimal substructure problem, and the longest path doesn't. And longest path actually is also a hard problem. And as you have seen in the first part of the lecture, the shortest path is a polynomial time solvable problem. Just a side remark, I just noticed, because we talked about longest paths before, and I just showed you a dynamic program how to solve this, and now I'm telling you this is a really hard problem. How does that go together? Any idea? How can both statements be true? So essentially, I'm telling you now I can't solve this problem using dynamic programming. But actually we did before. We used a dynamic program to solve the longest path in order to find the longest increasing subsequence. So what's wrong here? Yeah, exactly. So in the previous one, we had this very nice topological sorting, which meant that this graph is acyclic. And in this case, we make a statement about general graphs that can have the cyclic structure. And in this counterexample, actually we do have cycles. And this explains sort of this difference in hardness or complexity of these problems. Okay, so this is the sort of the introduction into dynamic programming. Before I start, any questions? Start with an example, a more elaborate example of dynamic programming. Yeah, no? Yeah. The shortest, I mean, for the shortest, this is not. Yeah. I'm not 100% sure I understood the question, but let me try to answer it, and you can tell me if I answered the wrong question. But the idea is that you're trying to solve, let's say, two problems, and let's say you look at the subpath from P to S and from S to R, and you would look at the longest path from S to R, which goes here, and then you would try to attach it to the longest path from P to S. But the longest path from P to S would reuse some of these vertices, and that's why they're not incompatible. So you cannot solve them independently, because if you solve them independently, you can't stick them together to a feasible path anymore. So that's sort of the high-level idea. Yeah? Okay. Any other question? Then let's look at an example, a very famous example that is very old but very elegant, very simple but very elegant. It's somehow always the case whenever you look back, it looks all very simple, but it's really sort of a milestone actually in this field, especially in bioinformatics. This is sort of the first application of dynamic programming in biology, in comparing biological sequences, which was proposed in I think 1970 or 71 by Needleman and Wunsch. And its purpose is to compare, in this case, biological sequences. This could be genome sequences, protein sequences, whatever sequence. It doesn't have to be biological sequences. It it does have also many other applications. But the goal is to really compare two sequences. And in our example, we look at DNA sequences, very short ones, so probably not exactly very realistic. But also this is not the point. So an example application now of dynamic programming is what we call edit distance, computing the edit distance between two sequences. And in this scenario, we're given, or in this example, I should say, we are given two sequences S1, and they're over DNA. So this is an alphabet of size 4. We have A, C, T, and G. And the first sequence looks like this. We have A, C, G, T, A. And we have a second string S2, which reads A, T, C, T, G. These two strings have equal length in this example, but generally they don't have to have the same length. Okay, so now if you wanted to compare these two sequences, you wanted to know what do these two sequences have in common. They have some A's in common, and I see a C that they have in common and a T. But how can I quantify this? How much do they have in common, and how much are they different really? So one way to capture this information, or the similarity or difference between two strings, is through an alignment. Has anyone heard of alignments before between strings? No, it's good. So here's one possible alignment of these two strings. Let's say if I start basically looking at the first character in these two strings, and I see these are two A's. So I'll write them basically in the same column on top of each other. And then next comes a C in S1, and it comes a T in S2. So they're clearly not different. And it's why I introduce what's called a gap in the first sequence and align it to the T. And I'll tell you in a second how this can be interpreted. And after having done that, I can proceed with the next character in S1, which is a C. And it's also a C in the second character. So we have found, again, two identical characters. Then I have a G in S1, for which I don't have a matching character in the second one. So I align it to this special symbol gap. Next comes two T's that I can align. And in the end, I align the remaining two characters, A and G. I could have done this differently. I could have done the following. I could have aligned the two A's again, but then instead of skipping one, I would just align a C with a T, and then skipping 2 in the first one, and aligning the 2 identical G's again, and then just proceed with the last 2 characters that I have to align with these gap symbols. So these are special symbols that are called gaps in these contexts. And then how do I quantify how similar they are based on such an alignment? Well, I would look at the columns in which the 2 characters or 2 nucleotides or whatever the characters represent, in which they are different. So the first example, I have an alignment. I see the A matches and the T matches and the C matches. But for the T, I don't have a match. So I have aligned it to the special symbol. The G, I don't have a match. And also for the last one, I have aligned A to G and they also don't match. So the cost I would quantify of this particular alignment as 3. And the cost of the second alignment would be, based on that, what is the cost of the second alignment? 2? No, why? So I have the C. I make a mistake with the second column, right? Because I align the C to a T. Then I make 2 more mistakes by aligning the C and the T to this gap symbols. And then I make yet 2 more mistakes by aligning the last 2 characters in the first string to nothing in the second. So overall, I make 5 mistakes, and the cost of the second alignment is 5. And why is this a meaningful interpretation? The way I just counted sort of the mistakes. Well, it can be considered as the number of operations, or specifically the number of substitutions, insertions, and deletions you would have to introduce into one string to convert it into the second string. So in the first alignment, the A already corresponds to the A. I don't have to do anything. Aligning a T to this special gap symbol essentially means that I have to either insert a T in the first string if I want to convert the first string into the second, or I delete it from the second string if I want to convert the second string into the first one. So let's say we want to convert the first string to the second one to keep it simple. So the A is okay. The second character, we have to introduce a T that's missing. That's what the second column tells us. The third column tells us we don't have to do anything. We have 2 matching Cs. The G is aligned to a dash in a second, so we have to delete it to make it identical. The T again is identical. We don't have to do anything. And the A is aligned to a G, so we have to substitute the A with a G to finally obtain a string that is identical to the second string. So you will need 3 operations, namely an insertion, a deletion, and a substitution to convert the first string into the second one. And that's why the so-called edit distance between, the cost of this alignment is 3. You don't have to. You can also say, well, I align the A to a gap symbol and the G then again to a gap symbol. But in this case, you would have sort of a cost of 2, which is sort of more expensive. So once you have done everything up to TT, there's not much more you can do. You only have these 2 characters left, and either you align them or you try to align them to a gap symbol. But the point is that you want to find an alignment, an arrangement of these letters and these special characters such that the distance is minimized. And the distance, the way I just explained it, by the number of operations that you need to transform one string into the other. And the second one, I said, has edit distance, or has, cost of 5, because I have to convert the C to the T. I have to introduce or insert a C and a T, and then I have to delete a T and an A. And that's why the cost of the second alignment is 5. And yeah. The last character in the first string or the second string? Yeah. The second string is ATCTA. Yeah, you're right. Where did I get this G from? ATACGTA. Yeah, okay. Did I do it in the correct in the first one? ACT. No, it's also incorrect. Okay. Then maybe I've done a mistake in writing S2. Let's make a G out of this. Yeah, I'll actually make it in blue, and you see that I changed something here. Also in my notes wrong. Oh no, the notes is correct. It's just me. Yeah, thanks. So we have two alignments, and every alignment has a cost, namely the number of operations, or in principle, the number of columns in which we have sort of mistakes. And the interpretation of this alignment is basically the number of operations you need to transform one into the other. And you see that this is symmetric because I told you we need 3 operations to convert the first one into the second one in the left example. But I can do the opposite whenever I do an insertion in the first, I do a deletion in the second, or the other way around, and get the same thing. And then I would convert the second string into the first one with the same number of edit operations. And the edit distance is then the cost of the alignment of smallest cost. So I try all these alignments, and the one that is sort of the cheapest will tell me the so-called edit distance between the 2 strings. So in this case, the edit distance between these 2 strings should be 3. I believe there's no other alignment that is better than the one that we show here on the left. And that's what's called edit distance. Let me just write this down. So in this case, we denote this by E subscript E for edit distance between our 2 strings S1 and S2, which is the minimal number of insertions, deletions, and substitutions needed to transform S1 to S2, or the other way around. In the first alignment, we said we had, so we can't call this edit distance because edit distance is really the minimum, but the cost of this alignment, on the left one, let me write this here in a different color. The cost of the first alignment we said is equal to 3. We have 3 columns with not matching characters, and the cost of the second alignment is 5 because we have 5 columns that don't match. And the edit distance in this example, the edit distance between these 2 strings, S1 and S2, is equal to 3. Good. Any questions here? So this is how we define edit distance. And now we're going to see how we can compute it using dynamic programming. So what's the sort of the best alignment of 2 strings? And it has lots of applications. I told you already in phylogeny, if you want to quantify the evolutionary distance between sequences, you want to find related genomes and many more. And the way to compute this is using a very elegant and simple dynamic program. And to do this, to solve this using a dynamic program, we first have to come up with the definition of subproblems. So how do we decompose now the problem of finding the best alignments between 2 strings S1 and S2 into smaller subproblems? Any sort of immediate suggestions just to see what you would come up with? So before we sort of said there's a natural way to traverse this from left to right, but we had only 1 string. Now it's a bit more complicated because we have 2 strings. But it's sort of a generalization of this idea. Well, we'll see that it will be helpful to consider prefixes of these two strings. So in order to solve the alignment of two strings, I look at all pairwise alignments of prefixes of these two strings. Now we'll see that this is much simpler. And you will also see that we can order these subproblems to, again, come up with a dynamic programming scheme to solve this dynamic program, to solve this edit distance problem. Okay, so let's look at the optimal substructure. And for second property, we said we need, in the case of dynamic programming, is overlapping subproblems. Did we say that? Oh, I don't see it. Yeah, okay, I forgot here at this point. Designing a DP. So this was what I wanted to do before I started this example. I mentioned the first point. The first point here is optimal substructure. What I forgot to mention is the second point here, which is overlapping subproblems. So let me, how do I do that? I can cut and paste. Yeah. So make a note here, please, that this goes in between here. Yeah, this I forgot. This down, yeah. Okay, quick recap to designing a DP. So here's what I forgot. The second part, after having sort of this optimal substructure problem, is to have overlapping subproblems. So let me just show you what that means. And it's an important property that we are sort of exploiting in speeding up this computation using dynamic programming. So that's called overlapping subproblems. And it simply means that if you were to solve the same problem instead of dynamic programming using a recursion, you would solve the same problem, the same subproblems over and over. So when a recursive algorithm, if you would use a recursive algorithm, it would encounter same subproblem over and over. So here's an example, and then we can go back to the example that we've been working on. So if you look at again, subproblem graphs, let's say the subproblem graph looks as follows. It's very similar, or maybe it's actually identical to the previous one. Do you remember what how to interpret this subproblem graph? This edges just indicates dependence on certain subproblems. Good enough. Then what you can see here is that, I mean, we said we try to solve this bottom up. So we start with the subproblem D. But if you would do it based on recursion, we would start top down. We would start with the problem A right away, and then realize that A needs to first solve B and D. So we would call basically the same algorithm for subproblems B and D. But once we're trying to solve B, we realize that we again have to solve D because B also depends on D. And we keep on doing this. B also will call C, and C again will call D. And in that way, you will see that solving all these problems, A, B, and C, they will call for solving the same subproblem D. So in this case, we will solve the same subproblem D multiple times in different paths of the recursion tree. And this is basically the scenario where we can benefit using a bottom-up approach in dynamic programming compared to recursive algorithms. In this example, subproblem D would be encountered in solving A, B, but also C. And think of the longest increasing subsequence. If you had a sorted array, you would have many edges that would point to a certain element, and you would use sort of the longest increasing subsequence ending at the second element whenever you calculate the longest increasing subsequence to any of the subproblems to the right, and you would resolve the longest increasing subsequence. And you can, and this would actually, in the case of a sorted array, this would lead to a recursion tree that has an exponential number of nodes. So in this particular case, we reduced this potentially exponentially large number of nodes in the recursion tree to something polynomial, because we can solve it, as we showed in quadratic time, n squared, using this bottom-up approach. So this is sort of the reason why this is for such kind of problems where we have to solve the same subproblem over and over, why dynamic programming is superior to a recursive approach. And this generally means that we can reduce something that might have exponential recursive time to a polynomial time dynamic program, which is the case for the longest increasing subsequence. Okay, so this is the part I forgot to include in these two ingredients. So this is the two things we need for dynamic programming: optimal substructure, and then have these overlapping subproblems to benefit really from this bottom-up approach compared to some recursive scheme. If there's no questions, I'll go back to the example of computing edit distance. So in edit distance, we wanted to describe these two things, namely the optimal substructure and these overlapping subproblems. I want to show you that in this particular problem, we have these two ingredients. So in this case, let's look for optimal substructure and overlapping subproblems. The first part is optimal substructure. Now for this particular problem of edit distance. And let's say that we want to have, that we have strings x and y. So x, the first string. So before we said S1 and S2, now we have x, which has length m. So it goes from x1 to xm. And we have a second string y that goes from, sorry, y1 through yn, so there's length n. And I suggested that instead of looking at the whole problem at once, we try to look at smaller subproblems that are sort of composed of prefixes of these two problems, of these two strings. So let's say we're looking at prefixes. You will see that this will allow us to solve this whole thing bottom up again. Namely prefixes that go from x1 through xi. So we take the first I characters of x and prefix of yi, sorry, y1 up to yj. So we take the first j characters of y, and I needs to be smaller or equal than m, the length of the first string, and j is smaller or equal than n, the length of the second string. And this is what we call subproblem P indexed by I and j, the length of the two prefixes. Okay, so this is our idea for a subproblem. We just look at the two prefixes of x and y. And now let's try to come up with an ordering of these subproblems and a relation that tells us how to solve one problem based on solutions of these subproblems. And useful is the following insights. Let's say that we have solved Pij, so the problem of aligning a prefix in x of length I and a prefix of length y a prefix of length I in x and a prefix of length j in y, just denoted Pij. Then let's look at the very last column of this alignment. How can the last column look like? So if you look at the alignment between first I characters of x and the first j characters of y, there's really three possibilities that we can have in the last column, namely which ones? Yeah. So without looking at what x and y look like in this case, but what would the alignment do? The alignment has three choices, right? We said we can either put xi on top of yj. Let me write this down. Or we can align each one of them to a gap symbol in the other, right? So the last column of this alignment will have one of the three following structures. It either aligns xi to a gap, or the other way around, that yj will be aligned to a gap, or it aligns xi to yj. Right? These are the three possibilities. There's nothing else that you can have in this alignment. Let's call this case 1, case 2, and case 3. And let's look at these three cases and try to quantify Pij based on these three cases. We have case 1, 2, and 3. What is the cost of the alignment Pij in the first case? Can you can you tell me, similar to the LJs, so similar to the equation that we had for LJ, we said it's 1 plus the max of all the LJs to the left. How would you now quantify the cost of Pij, given that you know that the last column looks as in case 1, where xi is aligned to a gap? What's the cost? Yeah. Yeah, so 1, exactly. So 1 for this alignment to a dash or to a gap. This contributes a cost of 1 plus, when you say everything to before it, meaning, and what is to the left in x in this case? So prefixes from 1 to I minus 1, exactly, because I is already there. So we have a prefix from 1 to I minus 1 in x, but in y we still have a prefix from 1 to j because we didn't use this yj character. So the cost in this case, we have contributes a 1 to the cost for aligning xi to the gap symbol, which we said corresponds to an insertion or deletion. So it's a penalty of 1 plus whatever the cost of aligning the two prefixes, where x of aligning, we said x x1 to xi minus 1 and y1 through yj. And what is that in terms of p? This is exactly p I minus 1j, right? This is the optimal solution to the two prefixes that go from 1 to I minus 1 for x and from 1 to j in y. Does that make sense to everyone? Okay, then if there's no more questions, I see you next week, and good luck with the exam. But there's actually one question, yeah? About what? Maybe, yeah, maybe you can talk about this then, and since it's too loud, yeah, and I stop in.